Dear students, in this video, let us study the design strength of tension members. Section 6 of IS 800-2007 provides details on the design strength. Actually, clause 6.1 gives information on tension member. The factor design tensile load T in the member should be less than the design strength Td of the member. The design strength of the member under the axial tensile load is the lowest of the design strength due to yielding of cross section, next fracture of critical section and block shear strength TDB. So now let us go through this one by one. Clause 6.2 gives information on design strength due to yielding of cross section. The design strength of members under axial tension TDG is governed by yielding of cross section is given by TDG equal to Aj into Fy by gamma m naught, where Fy is yield stress of the material, Aj is gross area of cross section, gamma m naught is the partial safety factor for failure in tension by yielding. It is given in table 5 of IS 800. Clause 6.3 gives information on design strength due to rupture of critical section. Here this design strength due to rupture values formulas are different for different members. Clause 6.3.1 gives design strength due to rupture of critical section for plates. For plates, this rupture strength can be calculated, that is TDN equal to 0.9 into AN into FU by gamma M1, where gamma M1 is partial safety factor for failure at ultimate stress. It is also given in table 5. Fu is ultimate stress of the material. An is net effective area of the member. This net effective area of the member can be calculated using this formula. If bolts are arranged in a straight line, the net effective area of the section can be calculated using the formula B minus N into DH into T. If the bolts are arranged in the staggered manner, this formula is used to calculate the net effective area, where B and T indicates width and thickness of the plate, DH is the diameter of bolt hole, G indicates gauge length between the bolt holes, PS indicates staggered pitch length between line of bolt holes, N is the number of bolt holes in the critical section, and I is the subscript for summation of all the inclined legs. The design strength for threaded rods, that is the strength due to rupture of critical section for threaded rods, can be calculated using the formula TDN equal to 0.9 into AN into FU by gamma M1, where AN is net root area at the threaded section. Similarly, for single angles, rupture strength can be calculated using this formula. The rupture strength of an angle connected through one leg is affected by shear lag. Therefore, the design strength TDN is as governed by rupture at net section is given by TDN equal to 0.9 ANC into FU by gamma M1 plus beta AG0 into Fy by gamma M0, where beta is equal to 1.4 minus 0.076 into W by T into Fy by Fu into Bs by Lc. It should be less than or equal to Fu gamma m naught by Fi into gamma m1, and this beta should be always greater than or equal to 0.7, where W indicates outstanding leg width. Here if you can see the length of W, this is the gusset plate and this angle is connected here. W indicates the length of outstanding leg. BS indicates shear lag width. It is also given here. BS is the shear lag width, that BS is equal to W plus W1 minus the thickness of this angle. Next, LC is the length of the end connection, that is the distance between the outermost bolts in the end joint measured along the load direction, or length of the weld along the load direction. For preliminary sizing, the rupture strength of net section may be approximately taken as TDN equal to alpha AN FU by gamma M1, where alpha value will vary based on the number of bolts. Alpha value is 0.6 for 1 or 2 bolts, 0.7 for 3 bolts, and 0.8 for 4 or more bolts along the length in the end connection or equivalent weld length. AN indicates net area of total cross section. ANC indicates net area of the connected leg. AN is the net area of total cross section. ANC indicates net area of the connected leg. This is connected leg and this one is outstanding leg. AG naught indicates gross area of outstanding leg. AG naught indicates the gross area of this outstanding leg, and T is the thickness of leg. And for cross 6.3.4 gives the value of TDN for other sections. Clause 6.4 gives information on the design strength due to block shear. The strength as governed by block shear at an end connection of plates and angles is calculated as given in clause 6.4.1. Clause 6.4.1 gives the block shear strength for bolted connections. Here the block shear strength TDB of connection shall be taken as the smaller of these two TDB values. Here the first TDB is equal to AVG into Fy by gamma m naught into root 3 plus 0.9 into ATN into Fu by gamma m1, or the other TDB, that is block shear strength, is equal to 0.9 into AVN into Fu by root 3 into gamma m1 plus ATG into Fy by gamma m0, where AVG and AVN indicates the minimum gross and net area in shear along bolt line parallel to external force respectively. ATG and ATN indicates minimum gross and net area in tension from the bolt hole to the toe of the angle. End bolt line perpendicular to the line of force respectively, and Fu and Fy indicates ultimate and yield stress of the material respectively. Similarly, clause 6.4.2 gives the block shear strength for welded connection. The block shear strength TDB shall be checked for welded end connections by taking an appropriate section in the member around the end weld, which can shear off as a block. These are some of the three strengths we have to calculate while designing the tension member.